Hello everyone, my name is Gong Sui and I'm one of the MAT students from Singapore University, Malaysia. Today, I will be giving a talk on L Hopital Rule, and here is the outline of my presentation. So first of all, I will be introducing some of the background of L Hopital Rule, and secondly, we'll be getting into our main statement, the L Hopital Rule, and thirdly, I will be giving a proof of L Hopital Rule, and lastly, I will be giving some examples on how we actually can apply L'Hopital rules on some limits problems. So now, without further ado, let's get into our introduction. So actually, L'Hopital rule was discovered by a quite famous mathematician, a Swiss mathematician, Johann Bernoulli, though it was named under L'Hopital. Well, historically, they believe that Bernoulli and L'Hopital actually have made some economy agreement, and L'Hopital actually bought some rights to Bernoulli's mathematical discoveries and published them in his textbook, as has shown in the following picture. The following picture is the original copy of the title page of the L'Hopital's textbook, and L'Hopital's rule was stated in the following textbook. Well, now why do we actually care about L'Hopital's rule? Well, in real life, most limits seems to be appear in the form of in the inter, indeterminate form. For example, what I mean by indeterminate form is like um infinity over infinity, 0 over 0, 0 times infinity, and so on. So this with the aid of L'Hopital's rule, we can solve this limit with indeterminate form easily, and also we can a finite result to achieve the goal solving our problems. Now, here is the main statement of L'Hopital's rule. Um, before we can apply L'Hopital's rule, we have to make sure our function fx and gx satisfy the following condition. The first condition is this: that as x approaches not fx approaches 0, and also similarly gx as s approaches s not equal to 0. Secondly is we have to make sure the derivative of f over g, f prime over g prime, and as s approaches s naught will be equal to some finite number. So yeah. So when these conditions are satisfied, we can conclude that limit uh, for the fraction fx over gx as s approaches s naught will be equal to L as well. This this theorem seems very powerful. For example, when we deal with some indeterminate form problems like sin x over x as s approaches 0, we actually can solve the limit problem by applying the L'Hopital rule, as we will be seeing that example as soon. Yeah. Now, before we get into the proof of L'Hopital rule, we'll be looking at some slightly weaker version of L'Hopital rule. So, what is the difference between this theorem and the previous theorem? So, L'Hopital rule is a generalized version which is a combination of right and left-handed limits. This theorem only care about the right-handed limit. Actually, it can be also it is actually a similar version to the left-handed limit as well. So scratch of the proof is like when we actually can prove this theorem, we actually can, without a loss of generality, we actually can get a similar result by proving the same similar argument for the left-handed limit. So actually we can then combine the both limit. Eventually we can get our desired result. That is the result of L'Hopital rule. Yeah. So now further ado, let's get into the proof. So yeah. Um so the first step is that on the condition one allows us to set Fa equal to GA and also equal to 0. So now applying the Cauchy-Mean value theorem, we actually we can get the following relationship, and we'll be looking at this, particularly this and this. Then we take the right limit, as well as we also can take the left limit. That's the proof for the left-handed limit version of the theorem just now. So now we'll be getting this. Eventually, we'll be getting this result. Yeah. Once we have gotten this result, we can find the both and left limits as I stated before. The similarly works work very similarly for the left-handed limit as well. Then we can combine these. We can get the following result, and also look here is that how we have learned in calculus 1 that when the right and left-handed limits both are equaling to the same finite number, we can actually conclude that this is equal to this. So eventually, we are done. That's roughly the scratch word of L'Hopital Rule. Though there are some technical things behind the proof, but yeah, that's roughly the scratch word. How we actually can prove L'Hopital Rule. Easy, right? Yeah. So now we'll be looking at some exercises. Just I stated before, we'll be looking at a very classical limit problem as when we have get involved in calculus 1. So we know from the geometrical proof of this limit, we know this limit is actually equaling to 1. So yeah, let's see we can get the same result by using the L'Hopital rule. Well, before we do that, let's try the direct substitution. We will be getting sine 0 over 0, and sine 0 is equal to 0. So yeah, we get an indeterminate form 0 over 0. Therefore, L'Hopital's rule is applicable to this example. We will now compute the derivative of sine x, and the derivative of sine of x will be getting cos x and 1. So now we'll obtain after substitution, we will be obtain cos 0 is equal to 1 as desired. So by L'Hopital's rule, we get limit of sine s over x as x approaches 0 will be equal to 1, just like what we have learned in calculus 1. It's actually the same. So yeah, now we'll be looking at another example, which are also I think quite common. So yeah, before we doing that, similarly we try to substitute s equals 1 into the numerator and the denominator. Now we'll be getting also as well 0 over 0. So now really applying L'Hopital rule, we will be computing the derivative of the numerator and the denominator. Then we'll be getting minus 1 over 2 minus x for the derivative of the numerator, and for the derivative of the denominator is quite easy. We'll be obtaining negative 1. Then after some cancellation and substitution, we'll be getting 1 over 2 minus 1, which is equal to 1. As how we have claimed in this statement. So this limit is actually equal to 1 by applying L'Hopital's rule. So see, this is the power of L'Hopital's rule. Without the app of L'Hopital's rule, we actually can't compute this kind of limit easily, and maybe we have to use some like Taylor expansion, or maybe we should to do for this classical limit, we'll be using some geometric mathematical approach. Yeah. So I think Hopital Rule is quite in conclusion is quite powerful and very powerful, I would say. Yeah. Versatile in mathematical research. I think even in other field like engineering, yeah, this is quite important theory. That's the end of my presentation. Thank you. See you guys next time. Bye bye.